Welcome, everyone. For today's prep, we're going to be looking at implicit differentiation. And we're not going to get to related rates just yet. We're going to first do implicit differentiation. That's what we're going to be looking at here. And to kind of set the stage for this new type of differentiation, we're going to first just briefly consider two different types of functions. So there's what we call explicitly defined functions. And this is basically everything we've looked at in the course so far has been explicitly defined functions. So as a quick example, y equal to x squared minus 1. That's the graph that we see here. That's an explicitly defined function. So what we're doing here is we have an equation of two variables, and we're saying y, we're writing y as a function of x. So we have a formula, y is equal to this. So it's in the form y equals. All right, so that's what makes it explicit. We're saying we're literally explicitly telling what y is equal to. And this is everything we've looked at in the course so far. Well, if we're considering equations involving two variables, we can have equations of variables that are not in the form y equals. And those we're going to consider as implicitly defined functions. And the idea here is these are not in the form y equals. So as an example, the graph of this circle here is given by the equation x squared plus y squared equal to 4. So this equation, it's an equation involving two variables, and it's not in the form y equals. We haven't solved this equation for y. Now, maybe it's possible that we could, and in this case we could actually solve this equation for y, but sometimes there's complicated functions or complicated equations where you can't solve for y. You're kind of stuck with the equation. And in cases like this, it's still possible to consider y as a function of x. So for an equation like this, we're going to think of x as just like a regular variable, but then we're going to think of y as kind of like two things. It's going to be a variable in this equation, but then we're going to also think of it as like there's x terms that are hidden inside of it. So this is a kind of a new way of thinking about functions. If we have an equation, we don't necessarily need to solve it for y in order to kind of look at some properties of that function. And one of the main properties that we're interested in a calculus course is, well, what is the derivative, dy dx? And in both of these cases, calculating the derivative dy dx, what is it going to give us? Well, it's going to give us the slope of the tangent line. This is kind of what we've done before. The slope of the tangent line at our point P. So in the first case here, we have this parabola, and then we're interested in this point P, and we have our tangent line. Well, how would we figure out the slope of that tangent line? We'd calculate dy dx. And normally, we would then have to evaluate that derivative at our x-coordinate to get the slope. Now, for the case of an implicitly defined function, the derivative dy dx is still going to give us, if we pick a point on our curve, so we graph the curve, pick a point on it, well, the derivative is still going to give us the slope of the tangent line at that point. The one exception is we're going to have to evaluate this at our x-coordinate, but sometimes we might also have to evaluate it at our y-coordinate as well. But in either case, the derivative, dy dx, is still giving us the slope of our curve, the slope of our tangent line at point P. Okay, so let's look at these variables a little bit more. So when we talk about the derivative, dy dx, the y on the top there, that tells us two things. We're viewing y as a function. That's kind of the main thing. We're viewing y as the function, but y is a perfectly good variable on its own. So when we differentiate, when we have a y term in our equation, we're going to think of y as like two things. We're going to think of y, first of all, as a variable, which, it is. It's kind of like x. But we're also going to think of y as a function of x. So whenever we see a y, so when we see that like y squared in that previous equation, we want to think of it as like there's x terms that are hidden inside of the y. So kind of something like this. We have the squared function, but then here we've actually explicitly stated what those x terms are. So we have them explicitly written here. Here we're just kind of almost like assuming that there are some x terms hidden inside of it. So it's implicit. It's kind of hidden inside. All right. Well then, what about the x? Well, that x in the denominator, well, not really a denominator, but the x that we see in the bottom there, x is, we're going to treat as just a variable, and that's it. Okay. So there's going to be a distinction here. When we have an equation involving two variables, if we're trying to calculate dy dx, the x is going to be treated as just a variable, just a plain old variable, just like we're used to. And y is going to have kind of two roles. So the way we do this, the way when we go to actually differentiate one of these terms, we're going to differentiate our x term just like usual. So that's it. If we have a term involving only x's, then just differentiate like usual. All of our derivative rules apply. No big deal. Now, if we have a term involving only y's, well, we're going to differentiate just like usual. I don't want two there. One. But then there's going to be a little bit more. So we're going to differentiate like usual, and that's because we're treating y as a variable. So x is a variable, and we're going to differentiate it like usual. Y is a variable, so we're going to start by differentiating it like usual. But then because we're treating y also as a function, we're going to multiply the result by y prime. So let's see why we would do that. So let's go up to the case where we have this kind of explicit function. And let's kind of practice that. So if we were going to differentiate this x to the fourth plus 3 squared, it's going to take chain rule to do that. So what would chain rule look like? Well, we'll call our derivative f prime, and we would bring down the squared, put it in front. We're going to keep the term inside the parentheses exactly the same, and then we subtract 1 in the exponent. So we don't normally write an exponent of 1. And then we take all the terms that are inside, and we have to multiply by their derivative. So that's chain rule. It's the derivative of the outer squared function times the derivative of the inner function, the stuff inside the parentheses. And then we would keep differentiating from there. Well, the same thing's going to happen with a y squared. If we tried to differentiate a y squared, it's going to be that same chain rule. Now the difference here is we don't actually know what those inner terms are. We're just kind of assuming that there are some inner terms involving x's. They're kind of hidden inside the y, and we can't see them. So how would the derivative look like in this case for this y squared? Well, we would start exactly the same way, though. We'd start by differentiating the power function. So we'd bring the 2 down, keep y the same, and then we'd subtract 1 in the exponent. We don't normally write a 1 exponent, though. And then, again, we're kind of viewing stuff as being hidden inside that y. We can't see it, so we're just going to multiply by y prime. So really what we're doing is, in each of these cases, we're multiplying by the derivative of the inner function, And in one case, we actually can see the stuff, so we could actually calculate that out. In the other case, we don't actually know what the inner stuff is. We're just kind of assuming it's there. And so we just kind of have to leave it as a y prime. Okay. So let's try an example. So let's look at that equation, x squared plus y squared equal to 4. We're going to actually calculate the derivative dy dx using this implicit differentiation. And let's go through the technique. So the first step is apply the derivative to each term of our equation. So let's write down our equation again. X squared plus y squared. Yeah, I'm going to use a little more spacing. X squared plus y squared equal to 4. And then we're going to apply the derivative to each term. Okay. So we're going to differentiate each term. All right, so the x term here, this involves only x's. So we're treating x as just like a regular variable, which it is. So we just differentiate that like usual. And in this case, we get 2x. Now the next one, the y squared, this term involves only y. So we're going to start by differentiating it like usual. So we get 2y. But then we differentiated a y term here. So we're going to multiply by y prime. And that's really kind of like a chain rule. So it's the derivative of the outer. And we're assuming that there's x's that are hidden inside the y. So we're multiplying by the derivative of the inner function. And then on the other side of our equation, derivative of 4, well, that's just a constant. So that's usual. Derivative of 4 is going to be 0. Okay, so that's the first step of our implicit differentiation. Apply the derivative and then calculate the derivative of each term. So the rest of the steps here in this implicit differentiation, let me get out of the way so we can actually see. Nope. Oh boy, what did I do? Well, I guess I can't. I think I changed the setting. So the other steps in this strategy here are solving for y prime. So that's usually the most difficult part of these, is to actually try to isolate y prime. So once we are done differentiating, the second step is we want to move all terms with y prime to the left-hand side of our equation. We want to move all terms then without y prime. We want to move those to the other side, to the right-hand side of our equation. So that's step 3. And then on the left-hand side, we're guaranteed, if we did it correctly, everything should have a y prime. So we should be able to factor out a y prime. And then we'll be able to divide both sides by that factor. So let's kind of see how those last 4 steps are going to work. And again, the calculus part is just step 1. Solving for y prime, probably the more difficult part of this, is steps 2 through 5. So let's go through those steps. All right, so, and it helps when you do this, you kind of want to think about, scan through the equation and think about, does the term have a y prime or doesn't it? So in this case, the 2x doesn't have a y prime, but the 2y times y prime does. So we want to keep this one on the left. It's already on the left, so we want to keep it there. But the 2x doesn't have a y prime, so we actually want to move this one over. And the way we move terms around like this in an equation is, in this case, we're going to subtract. So when we subtract, we're going to have 2y times y prime equal to negative 2x. All right. So that's steps 2 and 3. We've got all the terms now on the left have a y prime, and all terms on the right don't have y prime. So now, on the left, we want to factor out y prime. So in this case, if we factor out y prime, what we're left with then is just this 2y. So now we want to get rid of that 2y from the left side of our equation. So we want to move this over to the other side. And when it's being multiplied, the way we move terms is with division. So when it's addition, we do subtraction. And when it's multiplication, we do division. So now we're going to divide both sides by 2y. And that'll cancel it out on the left. So that'll do it then. Once we divide, we get y prime is equal to negative 2x over 2y. And in this case, we can simplify a little bit. The 2's cancel. And we end up with negative x over y. So you don't necessarily have to simplify, but it does make it easier for evaluation. So the derivative here is going to look a little different than the derivatives we're used to. Normally we're used to derivatives where there's only x's or constants, but now the derivatives with implicit differentiation are usually going to have both x's and y's. And the reason is because, well, we didn't actually know what the formula for y was. So, it's perfectly reasonable then, since we didn't actually solve for y, that our derivative is going to have some y's in it. All right, so let's actually use that derivative then to figure out the slope of our graph. And let's just do it at one point here. So at the point 1 comma square root 3. So slope of the curve at 1 square root 3 is going to be our derivative, the derivative we just calculated, the y prime that we just calculated. But now we're going to evaluate it at x equals 1, so the x coordinate of our point. And then we also have to plug in the y coordinate of our point. So this is square root 3. So we're going to, what did we find? It was negative x over y. That was the formula that we found for our derivative. And we're going to plug in these x and y coordinates. And you can kind of see this is why we normally have to plug in a y coordinate as well for our point, because normally our derivative is going to have some y's still in it. So if we plug in, we end up with negative 1 over square root 3. So I'm plugging in x equals 1 for the x, and then square root 3 there for the y. All right. So we're going to practice more of these in class. So we'll get some practice in. And what we're going to look at next with this implicit differentiation is, what do we do if we have a term that involves both x and y? So in this first one, there was only an x here, there was only a y here. They're kind of separated by addition. We're going to see what happens if we have, say, an x times x squared times y squared. So we'll see you then. Bye-bye.